In this video, we're going to talk about what we call series. We've already discussed what a sequence is. And basically, what a series is the sum of the terms of a finite or an infinite sequence. All right. And so all we're going to do is add up the terms, figure out what that sum of those terms are, and that will give us what we call our series. And so what we do when we write series is we use what we call summation notation. And summation notation is basically a shorthand way of writing out series. We don't necessarily want to write out all the terms of the numbers that we're always adding up. And so to do that, we use this notation here, this summation notation. Some people call it sigma notation, right? And the reason they call it that is because this symbol here, this is a Greek symbol for sigma. And that symbol represents the sum. So some people call this a summation symbol, but it is a Greek letter sigma. All right. This just means to add up, and I'm going to actually adjust this ever so slightly. And this just means to add up whatever you have sitting here, right? Notice here I have an I. This I is called our index. And it basically tells me what I'm changing when I add up these terms here. That a sub I is like our general term from before, which when we were dealing with sequences, we called a sub n. But here I'm going to have my index I, so I'm going to call this a sub I. And again, that's our general term or our formula that gives us all of our terms in our sequence, right? And so basically what this says to do is we're going to start from I equals 1. We're going to do the sum from I equals 1 to n, right? Now, we're always going to be dealing with natural numbers. My first natural number is 1. And so when I equals 1, wherever I see here, I'm going to replace it with 1, right? And so since I see an A with a subscript 1, I'm going to have A sub 1. My next natural number is 2. This sigma notation means to do a sum, so I'm going to add to that A, and now my next natural number is 2. Wherever I see an I here, I'm going to replace it with the 2. So I get my second term in my sequence. All right, plus I'm going to keep going. My next natural number is 3. So I get A sub 3 plus, and I will continue this until I get to my last natural number, right? Now, we know that a sequence can be finite or infinite. If it is finite, then this n is not going to be infinity. It is going to be some natural number, right? And that's going to be the last term in my series here. All right. If it is an infinite sequence, there is no last term, and this n here would equal infinity. We're not going to deal with the case where we have an infinite sum, an infinite series. We're going to deal with when we have finite in this section here. All right, but this just means to add up all of your terms, your first term, your second term, your third term, all the way to your last term of your sequence, right? This is just the notation for that. So they're equivalent things. This is the notation. I is your index. A sub I is your general term and is your last index value. All right. Now, sometimes you'll see your sequences, your series written with different actually different indexes. For instance, it doesn't have to always be I. For instance, sometimes we use the letter K equals 1 to n of A sub K. That's a K right there. And so that'll be A sub 1 plus A sub 2 plus we'll continue until we get to A sub n, right? So in this video, I'll be using I as our index, but your index can be any variable. Your A doesn't have to be an A. You know, you can use different variables. It just works this way. So what we're going to do is we're going to find the sum, right? We have this series here, and we're going to find the sum of this series, right? Remember, when we see the sigma notation, it just means to add up all of your terms. So this is our general term, right? We have a formula here. Instead of having A sub I, we have the formula for what A sub I equals, right? And so we're going to find that general term here. We're going to start with I equals 1, right? So this is saying do negative 1 to the first power times 2 times 1, right? Plug in 1 wherever I see an I. My second term is plug in 2, right? So negative 1 to the second power, we have 2 times 2, times 2 times 2. Then we have negative 1 to the third power times 2 times 3. plus negative 1 to the fourth power times 2 times 4 plus negative 1 to the fifth power times 2 times 5. And so these are the terms. We add up those terms together, and then the rest is just simplifying, right? So we know we have a negative 1 to the first power. That's going to be a negative, and 2 times 1 is 2. We have negative 1 to the second power, which is a positive 1, and 2 times 2 is 4. Here we have negative 1 to the third power, so I'm going to write that as a minus, and then that's going to be a 2 times 3, which is 6. And then we have negative 1 to the fourth power, which is positive, so I'm going to write plus. 2 times 4 is 8. And then we have negative 1 to the fifth power, which is the negative. I'm going to have a minus. 2 times 5, which is 10, right? So negative 2 plus 4 is 2. So this is 2 minus 6, which is negative 4, plus 8, which is 4, minus 10, which is negative 6. All right. And let me make sure I did that right. This is a negative 18, because if I combine my negatives, right, that's negative 10, negative 16, negative 18. And then 4 and 12 is positive. 4 and 8 is positive 12. 12 minus 18 is negative 6, right? And so we did that calculation correct. And so this is what this sum equals, right? So the sum from I equals 1 to 5 of negative 1 to the I times 2I equals negative 6. All right. So here I'm going from writing our sum, given our sigma notation for our sum, to finding the sum. And we can kind of go backwards, right? We can have a sum here, which is written in the terms that are in that sum, and we can write the series using sigma notation, right? And so when it says write it using summation notation or sigma notation, what we're going to do here is we're going to write it using the sigma symbol I equals blank to blank of our general term, right? So first, what I'm going to do is I'm going to look at these terms here, right? We know we're going to have the sum. I'm going to start, if I always start at I equals 1, right? This is my first term. This is my second term, third, fourth, fifth, sixth. So since we're adding 6 numbers, I know if I start at 1, I'm going to end at 6, okay? And now I got to figure out what my terms are. Well, notice we have in our sequence, right? We have 3, negative 6, 9, negative 12, 15, and negative 18. And so what we're going to see here is that we have an alternating pattern here. And so we're going to have negative 1 to a power. Notice that our first power is, our first term is positive. So I don't want this to be an odd exponent here on that negative 1. And so what I can do is I can write this as I plus 1 so that this is an even power when I plug in my first term, right? Plug in the first term, I equals 1, 1 plus 1 is 2. That is an even number. And when I raise a negative 1 to an even power, it's going to be a positive. And then the next one would be negative, and then so on and so forth. Excuse me. So I get negative 1 to the I plus 1. Now, notice here I have 3, 6, 9, 12, 15, 18. It's like we're counting by threes, right? And so this is basically a 3 times n. I plug in n equals 1, I get 3, right? I plug in n equals 2, I get 6. Now I'm ignoring the signs right now, right? So all I'm doing is multiplying this 2 times a 3, right? Here, when I do n equals 3, I get 9, right? So I'm multiplying the 3, which is my n, by 3. All right, when n equals 4, I plug in 4, multiply that by 3, right? So each of these n's are multiplied by 3, and so that's why my formula is times 3n. And one of the things that you notice here is that, and notice here, I made a mistake here. The mistake that I made was the fact that I use n instead of I. My index is I, n is my last number, right? So in the last, when we talked about these sequences here, we used n as our index or our subscripts. What we're doing here is we're using I now. And so I need to put that as an I instead of an n. So all of these are I's instead of n's. All right, easy mistake to make. All right, now summation symbols or notation does not always start at 1. For instance, I can allow this to start at 0, right? For instance, I equals 0, right? Now, if I let it start at 0, then I would be plugging in 0 first, right? So if I start at 0, this will be my 0th term. This will be my first, second, third, fourth, and fifth. So if I adjust this from 1 to 0, I've got to adjust this from 6 to 5. All right. So this is going to be from 0 to 5, right? Not only do I have to make that adjustment here, but I also have to make that adjustment in my general term, right? And so here, I'm going to have -1, right? Now, when I plugged in 0, I wanted to get a positive outcome, right? Notice here I had I plus 1. Well, if I plug in 0 there, I actually am going to get 0 plus 1, which is going to be an odd number. I need this first term to be even, this first exponent to be even, so that I can get a positive 3 there, right? And so I'm going to have to reduce or increase this in order to make this work, right? So I'm going to have I equals -1 to the either the I, or you can say I plus 2. So if I decrease this here, I'm going to raise this to the add 1 to this so that this is even. Not only do I have to adjust this part here, I have to adjust this part here as well. All right, because when I plug in 0, right? Well, 3 times 0 is not 0, is not 3, which is my first term. I need it to be 3. So what I'm going to have to do is I'm going to have to actually increase this I to be an I plus 1. Because when I plug this in, I need this to be a 3 times 1 instead of a 3 times 0. And so if I reduce this by 1, I've got to increase everything in my general term by 1. All right. And so this now becomes the sum I equals 0 to 5 of -1 to the I plus 2 times 3I plus 3. And notice here, when I do this, I plug in 0, I'm going to get 3. When I plug in 1, I should get 6 in this term right here, right? When I plug in 1 for I get 3 times 1, which is 3, plus 3, which is 6. When I plug in 2, I should get 9. 3 times 2 is 6, plus 3, which is 9, right? And so I know that I have this correct. All right, there are times when we want to start at 0. There are times when we want to start at 1. There are times when it's easy to start at other numbers when we're writing this summation notation, right? So be able to adjust depending on what case you use. And I know when we dealt with sequences, I said, oh, you'll do this a lot in calculus 2. There is a case in calculus 1 where we will look at series, right, in this summation notation. And it has to do with what we call integrals. And we'll see that in calculus 1. All right. And so with arithmetic sequences, series, right, this is basically the indicated sum of an arithmetic sequence, right? So remember when we had arithmetic sequences, I think we looked at the sequence 2, 4, 6, 8, 10. Well, actually, we looked at the sequence before of 14, if I'm not mistaken, 14, 16, 18, 18, 20, so on and so forth, right? We looked at this sequence here and we said that, oh, well, we can use the formula A sub n equals A sub 1 plus n minus 1 times d, where A sub 1 is your first term and d is the difference that is constant between your terms, right? So if I do 16 minus 14, I get a positive 2. If I do 18 minus 16, I get positive 2. And so that d would be positive 2. And so we could use that formula there to get our general term. And we ended up with 12 plus 2n as our general term there, right? And so that was our arithmetic sequence. Well, if we have a sum, if we wanted to calculate the sum of any arithmetic series, then what we can do is we can use this formula here, which is the sum equals S of n is the sum of n terms of that arithmetic sequence of n over 2 times a1 plus a sub n. All right, this is the formula that we use for our arithmetic series, right? And so your arithmetic series, again, are your sums of arithmetic sequences. If I know the number of terms in that sequence, if I know the first term and the last term, all I got to do is place those numbers into this formula, and it'll give me the sum of those n terms of your arithmetic sequence or series. And so let's look at this example here. It says find the sum of each arithmetic series. All right. I'm going to slide this over because I'm going to need some more space. All right, I have 2 plus 4 plus 6 plus, and I'm going to add all the numbers up until I get to 88. All right, that is the goal here. And so what I'm going to do here is we know that we are going to use this formula here, but we need to know, right? Remember, this is our first term. This is our last term. And this n here is the total number of terms. And so if you can look at this and find out how many terms you have here, then you're able to just directly substitute it into this formula, right? All we have to do is do S of n equals n over 2, a1 plus a sub n. Well, most of the times we have a lot of numbers and we don't know the number of terms, right? And so what we could use is this information that we already know, is that we know this formula here that allow us to find our general term in our arithmetic sequence, right? And so my a sub n, actually, that's our nth term there, and we actually know this value is 88. Our first term is 2. We don't know n, but we do know our d here, right? It's the difference between each term, right? And so if I do 2, 4, 6, 8, 10, 12, my d here is 2. This gives me, using this equation here for the general term of an arithmetic sequence, allows me to create an equation that just has our n as our variable, which is what we need to find in order for us to find the sum in this formula here. And so I get 88 equals 2 plus 2n minus 2. I get 88 equals 2n, divide both sides by 2, and I'm going to get n equals 44. And so now that I know my n, the number of terms I have here, which this might be, you might be able to figure that out in this example, but that'll be 44 over 2 times my first term, which is 2, plus my second term, my last term, which is 88. That'll give you a 22 times 90. And if I'm not mistaken, that is 1980, 1980. So if I add up all the even numbers from 2 to 88, I'm going to get a total sum of 1980. All right. And with this here, notice here, I placed the 88 here. If I wanted to write this in sigma notation, it would be the sum from I equals 1, and we just found that there were 44 of these. And our general term is basically this right-hand side of this equation here, right? Well, when I simplify it before I divide it by 2, that would be 2i. And now we know that that's the sum is equal to 1980. All right, so if we wanted to find this, we now have our information. All right, let's look at another example, which might be a little bit more difficult, given that we don't know the number of terms right out. Oh, let's undo that. All right, we have 1,000 plus 998 plus 996, all the way down to 88, right? And so our goal is to find the sum of this sequence, right? It is going to be n over 2 times the first term plus the last term. All right, I'm always wanting to say the last term, the second term. Remember, we could use our formula for our arithmetic sequence. And I don't know why, but I'm choosing the 2 units apart. Sorry about that, right? So given that this gives us a formula for our general term, right? So this is a general term. Now, I know I'm using a sub n. This stuff should actually use i's, since if I were using my sigma notation, I would have i's here. Don't confuse this a sub n with, don't confuse the n's, basically, is what I'm trying to say. All right, but here I have 88 as my last term. My first term is 1,000. I don't know my n. I need that in my formula here, which is why I'm going through this process. And then my d here is the difference, right? So if I do 998 minus 1,000, I'm going to get -2, right? Same thing as what I get when I do 996 minus 998, right? And so I'm going to solve this equation here, and I'm going to simplify things. And basically, my general term is given by this formula here, 1002 minus 2n, right? And so if I subtract 1002 from both sides, I'm going to get negative 114. And if I divide both sides by negative 2, I'm going to get n equals 57. And so my sum is going to be 57. There are a total of 57 terms here. I divide that by 2, and I multiply that by my first term plus my last term. That's 57 over 2 times 1,888, which is 53,808. And so, again, I could write this in sigma notation and say that the sum from I equals 1, and our n here is 57. 57. And our general form for our general term is 1002 minus 2 times I. Remember, if I plug in I equals 1, I get 1002 minus 2, which is 1000. If I plug in I equals 2, I get 1002 minus 4, which is 998, so on and so forth. So this gives me my general term in my sequence. All right. Again, we'll use these terms, these sums, and these series here. All right, and so this is what that S of n equals, and that's that 53,808, if we wanted to write it in shorthand notation. All right, we'll get to this in Calculus 1 more extensively, and then definitely you'll do a lot more with this in Calculus 2 if you take that course. But this concludes this video. I'll see you next time.